In this video, we'll give an introduction to supervised learning. We'll see a few examples of supervised learning problems, and in later videos, this will lead into developing our first learning algorithm. Let's start with an example. A few years ago, one of the students working with me collected a data set on housing prices. So we can plot that data set where on the horizontal axis, I'm going to plot the size in square feet of the house, and on the vertical axis, I'm going to plot the price of the house in thousands of dollars. So yes, 500 square feet, 1,000 square feet, 1,500 square feet, so on. And let's say this is a 100K, $100,000, that's $200,000, 300K, and so on. And we can take this data set and plot it like so, where for each house that went for a certain price, we plot a different cross, right? Just one data point per house. And now one question we might pose is, suppose I have a house that is, say, 750 square feet. How much can I expect to get for this house? And reasonable value looks like this. What, maybe a value around here? So maybe about $180,000. Oh, these housing prices came from Portland, Oregon, by the way. And so let's see. For a house of this size, how did I get the number 180,000 square feet? Well, one way we could have done that is if we had, say, fit a straight line to this data, which maybe looks like that. Then from this value, I could have, gone up and read off this value, $180,000, 180K from the horizontal axis. But then again, maybe, here's something else we could have done, which is rather than fit a straight line to the data, looking at this data, maybe it would have been better to fit a quadratic function, right? Because maybe the housing prices are leveling off a little bit. And, well, that's my quadratic function, which maybe I could have fit to the data instead. And look, if you do that, it looks like maybe I can actually get a little more for this house. To introduce a bit of terminology, it turns out this problem, or this sort of problem, is one example of a supervised learning problem. And the term supervised learning refers to the fact that we're given a bunch of right answers in our training set or in our data set, and our goal is to predict more of these quote right answers, where by right answer I mean for each of the houses in this data set we're told what was the actual correct price that house sold for. And our goal is to, given a new house, to predict the new right answer for this new house that's 750 square feet. To introduce another piece of terminology, it turns out what we just saw was an example of a regression problem. And the term regression refers to the fact that we're trying to predict a row-valued quantity. Okay, so maybe the price of a house is always a whole number of dollars, or maybe it's always a dollar and a whole number of cents. But we can think of, it makes more sense to treat the price as just a real value, any positive number, say. And as a regression problem, we want to predict a real value quantity. Here's another example of a supervised learning problem. A few years ago, I had some friends that were working on breast cancer, and in particular, on predicting whether or not a tumor is malignant or benign. And so let's see, on the vertical axis, I'm going to plot whether or not a tumor turns out to be malignant, meaning it's a harmful, cancerous tumor, or if it's not malignant, we call that a benign tumor, which means it's not a harmful tumor, informally. And so malignancy takes on two values, either 0 or 1, with 0 corresponding to no and 1 corresponding to yes. And on the horizontal axis, let's say we plot the size of a tumor, and then we can have a data set that maybe looks like this, right? Maybe we have a few tumors here that turn out not to be not to be malignant, so we plot them as 0. And we have a few tumors in our data set that unfortunately turn out to be malignant or harmful cancerous tumors, and then we plot them as 1s. And a problem that we might face is, if you have a patient that comes to you and that they have a tumor size that's the size indicated by this green arrow on the horizontal axis, you might want to ask, how likely is it that their tumor is to be malignant versus benign? Okay? So this is one example of, and this is another example of a supervised learning problem, because in your data set, you're told for each of these tumors whether it's malignant or benign. And it turns out that this is a classification problem. And I want to contrast the term classification with regression. And in the classification problem, we want to predict a discrete valued output. Okay? And in this example, the discrete valued output we want to predict is either 0 or 1. Or more generally, if you have a small number of discrete value outputs, for example, if you have, say, 3 different types of cancer, so you might output 0, 1, 2, or 3. No cancer, or cancer type 1, or cancer type 2, or cancer type 3. We'd also call this a classification problem. But to contrast this with a regression problem, where the goal is to predict a real value, whereas in classification problem, we have a small number of discrete values that we're trying to choose amongst. Let me take this data set and replot it in a slightly different way. So on this one axis, I have my tumor size as before, but instead of plotting the values as 0 or 1, I'm going to use 2 different symbols to represent malignant and benign cancers. So I'm going to use O's to denote non-malignant, or the value 0, so benign tumors, and I'm going to use red crosses, like so. Let's see, am I copying that right? 1, 2, 3, 4. Right, you get the idea. So I'm just taking all this data and mapping it down onto one axis using my cross and O symbols instead. And as usual, our supervised learning problem is given a data set that looks like this. If you have a new patient, to predict the odds, say that they have a benign tumor versus a malignant tumor. So far, in all the examples we've looked at, we were looking at only one attribute or one feature, such as tumor size, or in the previous example, the size of a house in a square foot. Or we're looking at just one attribute or one feature to perform our regression or classification task. Sometimes we'll look at multiple features or multiple of these sorts of input attributes. For example, we may have to continue the breast cancer example, we may have the tumor size as well as the age of a patient, and I'm sort of vastly oversimplifying this data set, but this is a real problem, of course. But for example, in this sort of somewhat simplified simplified data set, maybe you have a data set that looks like this, where all the O's I'm using to denote benign tumors, and all the crosses I'm using to denote malignant tumors, like so, say. Right? And this would be an example of a supervised learning problem where you have 2 features, tumor size and age, rather than just one feature or one input attribute, the tumor size. And maybe a learning algorithm will fit a straight line to this data and try to separate the malignant and benign tumors as well as you can. Then if you have a feature, if you have a new patient show up and their tumor size and age falls at this point, you may tell them that they have pretty good odds. Whereas if their age and tumor size falls over there, you may tell them that they're more likely to have a malignant tumor. This example used only 2 features to 2 attributes. One of the challenges with supervised learning would be to deal with how to deal with many more features. So for example, let's see, clump thickness and uniformity of cell size. These are the features that I guess friends of mine working on breast cancer actually extracted. Uniformity of cell shape, and more generally, you can come up with a lot of additional features or a lot more attributes with which to try to predict malignancy and benignness of a cancer. Okay? So hopefully that gives you the understanding of what supervised learning is, where you're given a data set and you're asked to predict more of these right answers, and of regression, where you have a continuous value output, and classification, where you have a discrete value output. I'm going to wrap up this video with a quick quiz question, which is, suppose you're running a company and you want to develop learning algorithms to address each of two problems. In problem one, you have a large inventory of identical items, say thousands or tens of thousands of items, and you want to predict how many of them will sell. And in the second problem, you'd like a program to examine individual accounts of your customers, and for each account to decide if that account has had its password stolen or if that account has been hacked or compromised. So for each of these problems, would you treat it as a regression or as a classification problem? The video will pause in a second, and when it does, please use your mouse to select one of these 4 radio buttons on the left-hand side. Please click on what you think is the right answer. Hopefully you got that the right answer is this third problem, where problem 1, if you have a large inventory of identical items, then if you have thousands of items, then you're trying to predict a real value. Think of it as a real value, the number of items you sell. Whereas in problem 2, the output is really either 0 or 1, whether or not the customer account has been hacked, and so we usually treat that as a classification problem. So that wraps up this video, and in the next video we'll go on to develop our first learning algorithm.